Hello and welcome to this video where we will continue our discussion on R analytics. As we can see on our Excel screen, we have some data pertaining to variables X, Y and Z. 10, 20 and Delhi are the values that are assigned to the variables X, Y and Z respectively. A variable can have a single value or multiple values. Here, the variable binder has numerous values that it can take, a different one each month. All these variables on this tab can take multiple values. All the values are stored in these variables and these variables are stored in a table. We have multiple tables stored on different Excel sheets, which in turn are stored in an Excel workbook. R, or for that matter, most programming languages have a similar structure. In R, these values, variables, tables, sheets, workbook, or say this column, which is a range of values and variables, are called objects. The lowermost in the hierarchy of objects are values or the data. In R, there are various data types. These can be integer, numeric, character, logical, and complex. Characters are also sometimes called string. String is a group of characters. Let us see examples of each of these data types. Logical data such as true or false, integer as 2, 5, 6. Numeric can be all numbers which are real and will include decimals as well, say 2, 2.0, pi, etc. As we have learned in the previous video, integer is essentially a subset of numeric. Then complex will have imaginary numbers such as 1 plus 4i. Characters will be alphabets and symbols other than numbers. This data can be stored or displayed in 6 types of data structures which are enlisted here. Vectors, lists, factors, matrices, data frames and arrays. Remember that these data structures are objects, and the data stored in these structures are also objects. The first type is vectors. Vectors are objects which store in one dimension and hence can save only the same type of data, say values of only one variable. For example, variables x, y and z have only one value, or these variables have multiple values but of the same type. If one is numeric, then all must be numeric. If one is character, then all must be characters. Also, we said that vectors are one-dimensional. That is, it will either be in a single row or single column. This kind of data is called two-dimensional. Vectors cannot store this form of data. Let us open RStudio and on the console type A is equal to 10. To execute this row, press enter. Remember, right now we are working in the console, hence we will press enter to execute the command. When we execute one row, then we obtain the value of this variable A. We can check the class of this variable by writing class and in brackets A. When we press enter, it gives the class as numeric. Let us now check the type of A by writing type of and in brackets A. We press enter and see that it is double. A double is any real number which is stored in double precision floating point format. Let us try to understand what a double precision floating point is. It is a computer number format which occupies 8 bytes of memory and can store a wide dynamic range of values. Double precision means that it has more precision by having more digits to the right of the decimal. Since every integer is a real number, each integer can be stored as a double. By default, R will show the class of every number as numeric and not integer, and the type of every number as double. Let us now write another variable b equal to Delhi. Since Delhi is a text variable, we write it within quotes. Press enter and we will get the value of b, which is Delhi. Let us now check the class of b. We see that this is character. Type of b is also character. So far, we have only stored single values within a particular vector. Let us now suppose that we wish to store multiple values. To do that, write d equal to c bracket open. Please note here that c stands for combination of. C is the alphabet that we use when we want to store numbers as vectors in a variable. This is why we did not name the variable c in order to avoid confusion. If you wish, you can name the variable c as well. Within brackets, we can store multiple values, say 2, 4, 1, 6, 5, 7. Press enter and we get the values stored in D, which are also known as elements of D. Now define another vector E equal to a combination of 2, 4 and 5. Now if we add a scalar 2 in D and press enter, we see that the scalar 2 is added to all the elements of D. Please remember that if we add, subtract, multiply or divide any scalar to a vector, then this operation will be performed on all the elements of the vector individually. Let us now add vectors d and e. Please see the result that we have obtained. 2 plus 2 gave us 4, 4 plus 4 gave us 8, and 1 plus 5 gave us 6. After that, the remaining elements of D got added once again to the elements of E. 6 plus 2 gave us 8, 5 plus 4 gave us 9, and 7 plus 5 gave us 12. Remember that for this to happen, D has 6 variables and E has 3 variables. For any arithmetic operations to be performed, the two vectors must either be equal or the longer vector must be a multiple of the shorter vector. If the two vectors added are not equal and the one is not a multiple of the other, then the command will not be executed. Let us see an example of that. Define f equal to the combination of 1, 3, 2 and 4. Write d plus f. We get a warning message saying that the longer object length is not a multiple of the shorter object length. Here, the longer object is d, which is of length 6, and the shorter object is f, which is of length 4. And since 6 is not a multiple of 4, this command is not being executed. We will discuss more about vectors, its elements and other features and properties in the next video. For now, we are just getting an overview of what vectors are. So we have learned that vectors are one-dimensional variables and store data of the same type. Let us now look at the next data structure, which is a factor. Factors are the data objects which are used to categorize the data and store it as levels. They can store both strings and integers. Let us see what we mean by categorizing. From your previous knowledge of statistics, you may know that there are three types of data: categorical, also called nominal, ordinal, and interval. Categorical data is where there is no intrinsic ordering. An example of categorical data is, say, males and females. Here, there is no requirement to write male data first or female data first. Any order will do. Then we have ordinal data, where we rank the data we have by first, second, and third order, for example. Here the order cannot change. Another example is slow, fast, and faster. The order remains constant and cannot be used interchangeably. Interval data is one which is allocated by fixed intervals. For example, salary may be classified as being between 20,000 to 30,000, 30,000 to 40,000, and 40,000 to 50,000. Here we have fixed intervals of 10,000 each. Hence, factors are those objects in which we store the first type, that is, categorical type of data. The second important feature of factors is that data is stored as levels. Let us look at the example where we take a vector g equal to the combination of grade A, grade B, grade C, grade D, grade B, grade A, grade C. Please remember to put all these grades in quotes as these are character values. Now say we want to store g as a factor. We write factor and then write everything else within brackets. When we now execute g, we see that we get all the elements in one row and then all the four levels A, B, C, and D. Levels are nothing but the categories in which the elements can be divided into. Similarly, we define H is equal to factor of combination of male, female, female, male, male. Now when we check for H, we get 5 elements in the first row and then both categories male and female in the subsequent one. Thus, the factor data structure can help us make categories or create groups in a given data set. We will go in much more detail about factors in the subsequent videos. Next up is matrices. Matrices are data objects where we can store data in 2 dimensions. Generally, they store integer or numeric values. One important thing is that all the values in a matrix should be of the same type. To create a matrix, we will have to first insert the values through a vector and then mention that in which dimension the data should be displayed. Let us look at an example. We write I is equal to 1 to 12. When we execute this code, we can see that I has 12 elements. This kind of data is known as sequential. Now, how do we convert this into a matrix? For that, we write mymat, which is the name of our matrix, equal to matrix and then open brackets. We write E here. Remember, we had created a vector E earlier with 2, 4 and 5 as elements. If we press enter here, then a column vector is generated as can be seen here. So a matrix with 3 rows and 1 column will be generated. Similarly, we write I here. If we execute this command, then this is the result we get. It will put all the elements in a single column, hence a column vector is made by default. There are 12 rows and 1 column in this matrix. This is why it is called 2-dimensional. If we want to specify the number of rows and columns, we can do that too. That we write, say, mymat2 equal to matrix, open bracket, we type I, and then n row equal to 4, and finally n col. Before assigning any number to n col, we must keep in mind that the product of number of rows and columns must be equal to the total number of elements. So if we have 12 elements in I and 4 rows, then we will have to specify the number 3 for n col. Now when we execute mymat2, we get a 4 by 3 matrix in front of us. One important thing to notice is that the elements are assigned to the matrix by column. This means that the elements will be assigned to column 1 first, and then once the number of rows get exhausted there, will the elements in the second columns start to populate. It will then go to the third column. If we want the matrix to be assigned by row, then we will have to mention it in the brackets that by row is equal to true. Now when we execute this command, we can see that the elements have been arranged row-wise. In later videos, we will see more details about how to work with matrices in R. An Excel file is also nothing but a matrix. The binder column is a vector, and so is the month column. However, the month column can also be stored as a factor because months can be treated as different categories. The next data structure is arrays. Arrays can store data in more than 2 dimensions. To see an example, we name the array as myArray and put it equal to array, brackets open. We write I since that is where all the elements are stored. After that, we have to mention the dimension. For that, we write dim is equal to 4, 3 and 2. 4 here denoted the number of rows, 3 is the number of columns, and 2 is the number of matrices. This means that this array will generate 2 matrices of 4 by 3 dimension. Now when we execute this, we can see we get 2 matrices of 4 rows and 3 columns each. Next thing we look at is data frames. Most of the work in R is done through data frames. A simple example of a data frame is the table we see here in Excel. The definition of data frame is, it is a 2-dimensional data structure or table in R which has each variable of equal length. This means all the columns will have the same number of records. However, it may be possible that some variables have missing values in some records. Thus, data frame is a table in R which stores a lot of vectors in it simultaneously. These vectors can be numeric or text type. There may also be factors in a data frame. Let us see an example. We write J is equal to combination of Delhi, Mumbai, Chennai, Kolkata, Noida. This is a vector. We define another vector K with values, or let us make it sale, with values 30, 50, 45, 67 and 80. Lastly, we define another vector by the name days. In that, the values are Monday, Tuesday, Wednesday, Thursday and Friday. Therefore, we have created 3 vectors, J, sale and days. Now we create a data frame by the name myFrame. We write myFrame is equal to data dot frame, brackets open, and then we mention 3 vectors J, sale and days. We see that an error has popped up. This happened because these are case sensitive. When we defined the vector, S was capital and here we wrote it as small s. So we changed the case to capital S. Now we execute the command to see how the data frame looks like. We can see here that there is an issue. While defining the arguments in a data frame, we cannot use combination of. We have to simply mention the 3 vectors directly. Now the data frame looks perfect. It has 3 columns J, sale and days as expected, with the values mentioned beneath the respective headers. This is how a table can be created through data frame. We have a lot of data frames inbuilt in R. If we just write data and put open close brackets after that, then we can see we get a list of data sets here. These can be used by us for practice purpose. For example, we have a data set on biochemical oxygen demand. So if we write BOD here and press enter, we can see that the data stored in this data frame is right here. Similarly, we have a data frame by the name Titanic. If we press enter, we can see all the values in this data set here. We can see another data frame by the name Orange over here. Like this, we can keep checking for the list of data frames present in R. The files that we import from Excel or CSV format are also treated as data frames by default. Last data structure is list. List is that container where we can store the rest of the data structures. You can think of it to be a workbook which has various sheets, each of which may contain a vector, a matrix, an array, a data frame, and so on. For understanding, we'll make a list and store all the data structures that we have created in it. We can see we have created a vector such as E, a factor by the name G, mymat named matrix is present, and a data frame by the name myFrame is also there. So we write mylist equal to list. In the parenthesis, we will mention everything we want to store in that list, be it a vector, a factor, a matrix, or any other data structure. So we have saved or stored all these things in a list named mylist. It is a very useful data structure when we deal with large data sets or models where we deal with different data structures. List then serves like a folder to us where we can store all these important things together. Now when we execute mylist, we will be able to extract everything that we had stored in it. We can see the value myData is displayed, vector G's elements are displayed, myFrame named data frame that we created is shown here, and lastly, mymat matrix is also given here. Now if we write mylist and put the number 3 in square brackets, then it will display the third element in the list, which was the data frame. We can go up and confirm that indeed the third element was myFrame, which was a data frame. We will go in more detail about data frames in the upcoming videos. This is it for this video. Thank you.